Hey everybody, this is Try Dying to Live here, doing a post-mortem on our video about the different staging methods, kind of answering some of your guys' questions, as well as showing some other experiments that I did. I actually did a lot more experimenting than you guys saw in the video. I condensed it down to very basic information. But it's kind of interesting. I tried these little guys here, which travel much slower and also are a little bit more efficient, and I got much larger numbers. All of the different staging styles get over 2,000 meters per second and get over 500,000 kilometers as a maximum height. So there's a huge difference in these guys here. Now the asparagus style still wins out. However, the serial versus the parallel styles, they actually start to even out and they become very similar. But some of you guys asked, why are some methods more efficient than others? And more importantly, we thought too that the parallel method would have been better than the serial method, but it didn't turn out that way. Well, there's a few reasons why, and I'm going to explain it very simply this way. There are things that add to your speed, and there are things that take away from your speed. And of course, engines add to your speed, and that's about it in various ways. You know, ion engines, rocket engines, RCS, jet engines, doesn't matter. Some sort of engine adds to your speed, but two things take away from your speed. One is gravity, and the other is drag, and they work very, very differently. So imagine it this way. We fire a rocket and it adds 10 meters per second of speed. Okay? Now gravity takes away 9.8 meters per second, give or take, 9.81, whatever. But the farther away you are, the less it takes away. So you think to yourself, I want to get away from Kerbin as fast as possible, because every second that ticks by, it's subtracting whatever the gravity is. So, you know, you start off and it's 9.8, you go up a few meters and it's 9.75, you go up a few more, it's 9.6, you go up a few more, it's 9, you go up a few more and it's 8.5, and so forth. So you want to get away from Kerbin as fast as possible, because every second gravity is taking away from your speed. Now you keep adding to it, so you're going to go faster and faster, but you know, that's why you kind of accelerate a little bit more when you're farther away from Kerbin than when you're closer to it. That's one of the reasons. The other reason is drag, and the way that drag works is simply this. You take the coefficient of the amount of air and the aerodynamics, and those work together, they're intertwined. You call them the coefficient. I'm not a physicist, so if I mess up, just be gentle with me. They work together, and the faster you go, the more drag slows you down. And it works out essentially to this, that every time you double your speed, you quadruple your drag. So for example, at say 10 meters per second, it subtracts 1 meter per second of drag. But at 2 meters per, or I should say at 20 meters per second, it subtracts 4 meters per second of drag. So every time I go faster, I lose more speed. And that's why, excuse me, that's one of the reasons why race cars and fast cars and whatnot can only go so fast, because they start slamming into the air so hard that they simply cannot go any faster, because they're pushing against basically a wall of air. There's also friction and some other things going on, but that's the biggest parasite why cars max out at about 250 miles an hour unless they are specially made. So what does this have to do with everything that I'm telling you right now? Well, what this means is the faster you go, the more drag affects you, and the slower you go, the more that gravity affects you. So the goal in all this is to figure out what is the best balance. And so, for example, the parallel, it fights gravity very well, but because it pushes so fast, if you have a light ship, drag is going to reduce the speed more. The serial, however, because it burns a little slower, it doesn't do nearly as well against gravity, but it doesn't fly so fast that until it gets into thinner air, it doesn't lose a bunch of speed. It doesn't lose a lot of efficiency. Basically, the fuel isn't wasted turning itself into drag. Now, why is the asparagus so efficient in this particular experiment? Well, the reason why is it combines the best aspects of fighting gravity, that is, quickly accelerating away from the surface of the planet, with the best aspect of fighting drag, which is not in fact going slow, but by reducing that coefficient by making itself smaller. So it gets itself going away from the planet quickly, which is going to raise drag, but it burns through that first set of tanks. And so actually when it starts off, it's actually not any better than the parallel, but it drops off those tanks, and suddenly you have the getting away from Kerbin, less gravity effect, and you have a smaller ship, so you're actually even lighter, which is going to help out too, but also you're going to have a significantly smaller aerodynamics. And so if you imagine here that there are 7 segments to the ship essentially, I guess there's a center one here, you are you're removing a little less than 2/7 of the drag, and that is going to make a huge difference, because you remember that drag is fairly exponential. All right, so that's something that you got to keep in mind. So that's why the asparagus is so effective, is because it balances that too. Now, if you're in a situation where you need a heavy lifter, the asparagus is not going to work as well, because suddenly, instead of burning from 7 engines, suddenly you're burning from 5, which makes it even worse than the serial staging method. So it's really great for fast ships because you're getting away, you're dropping off, as much excess as quickly as possible. But it's going to be fairly underpowered once your engines or once your fuel tanks start running out of fuel. So that's kind of a little bit of a post-mortem for you guys. Some of the reasoning why all of this, why the experiments worked out the same way, the different ways. So what this also tells you, and I want to convey to you, is depending on your ship, depending on what it needs to do, depending on its design, different styles are going to be better. So you might find that you have a heavy ship, and you say, hey, asparagus is not working out. Hey, serial is not working out. Hey, parallel is working great. That's part of the reason why the Delta rockets, the Delta V rockets, are a parallel design. Not very similar to what we do here, but it is in fact a parallel design. It is actually also a serial design as well, but they start off as parallel. The Space Shuttle, which has a great lifting capability, it also used a parallel design, and so you have all these wonderful things that it had as options. Now, of course, you say, well, a lot of the early, Apollo missions and Mercury and Gemini, they used serial. Yeah, they did. But you also look at some of the new, the Soyuz, and they also use, some of them use the parallel as well. So, it's got its trade-offs, it's got its goods and its bad. And so you might find that you have a rocket that doesn't work, like, you've built your launch vehicle and it just isn't right, and you say, well, I'm using the asparagus, why isn't it working? Well, go ahead and try a parallel, that onion cell. Go ahead and try serial. See what happens when you try out the different methods. You might find that, hey, what I need is not something that fights drag, maybe I need something that fights the gravity. And maybe instead of saying I need something that fights gravity, you say I need something that's a little more efficient, that's going to not shove my ship up so much. Another thing you can look at is usually we run our ships at full blast, and sometimes you're going to need that. You'll have a heavy ship and you need to run it that way. I did find out, I did a little experimenting, and I found out the ship actually runs a great deal more efficiently. This particular design with these shorter tanks here actually runs a great deal more efficiently if I run the power at 3/4 instead of all the way. Why? Well, because it's pushing too much against the air, and it actually that fuel is wasted because the drag is slowing us down. And so if we slow ourselves down a little bit, there's less drag, and we use that fuel later on. So I hope this was helpful in clearing up some of the thoughts and some of the questions you guys had from the previous video. Thank you guys so much for watching. I'll see you guys next time.